Welcome back. In our previous lecture, we explored the physical movements of molecules. We discussed how chemical bonds vibrate through stretching and bending motions, and how these motions absorb infrared radiations. But now we will take the next step. Today, we will connect those vibrational motions to a specific functional groups. In other words, we will learn how the vibrations of different chemical groups create unique spectroscopic signatures. This is one of the most powerful aspects of the infrared spectroscopy because once we recognize these signatures, we can quickly identify the functional groups present in a molecule. So let's begin. Let us first look at symmetric and asymmetric stretching in real functional groups. These are among the most common features in IR spectroscopy. For example, consider a methyl group, that is CH3. In this group, carbon atom is bonded to three hydrogen atoms. These bonds can vibrate in different ways. One important motion is symmetric stretch. During symmetric stretching, all the hydrogen atoms move in a phase. That means they expand and contract together at the same time. This motion typically absorbs infrared radiation at around 2872 centimeter inverse. Now compare that with the symmetric stretching vibration. In this motion, the bonds move out of phase. One bond may be stretching while another is compressing. This motion is more complex, requires more energy. As a result, the absorption occurs at higher wave number, around 2962 centimeter inverse. So let us look at another example, the anhydride group. Anhydrides contains two carbonyl groups connected through an oxygen atom. Because of this structure, the molecule shows two strong carbonyl stretching bonds. The symmetric stretching vibration appears around 1760 centimeter inverse, but the asymmetric stretching vibration occurs at slightly higher energy near 1800 centimeter inverse. This pair of peaks is often used as a diagnostic feature to identify anhydrides in IR spectra. Next, consider the amino group, that is NH2. This group also shows both symmetric and asymmetric stretching vibrations. The symmetric stretch typically appears around 3300 centimeter inverse. The asymmetric stretch occurs slightly higher, around 3400 centimeter inverse. These peaks are often broad due to hydrogen bonding effects, which we will discuss later in this course. Another classic example is the nitro group, that is NO2. The nitro group produces two strong IR absorptions. The symmetric stretching vibrations occur around 1350 centimeter inverse, whereas the asymmetric stretching vibrations occur at 1550 centimeter inverse with a gap of nearly 200 centimeter inverse. These two peaks together form a very characteristic pattern. When you see this pair of absorption, it strongly suggests the presence of nitro group in the molecule. Now step back and observe the pattern. Across all these functional groups, something very consistent happens. The asymmetric stretching vibrations always occur at higher wave numbers than the symmetric stretch. Why? Because asymmetric motion is more complex and requires more energy. So, whenever you analyze an IR spectrum, you should always expect the asymmetric peak to appear at higher energy. This simple rule is extremely helpful when identifying functional groups. Now, if IR spectra only contain these basic stretching and bending vibrations, interpreting them would be quite simple. But real IR spectra are more complex. When we examine actual experimental data, we often see extra peaks that cannot be explained by simple vibrations. These additional features arise from quantum mechanical effects. Let us explore some of the most important ones. First, we have fundamental absorptions. These are primary peaks we usually focus on when analyzing spectra. A fundamental absorption corresponds to a transition from ground vibrational state to the first excited vibrational state. In quantum mechanical notation, this transition is written as nu is equal to 0 to nu is equal to 1. These transitions produce the strongest peaks in an IR spectrum. Most of the characteristic functional groups absorptions we discussed earlier are fundamental vibration. However, quantum mechanics allows for other types of transitions as well. One example is the overtone. Overtones occur when a molecule absorbs energy corresponding to multiple vibrational quanta at once. For example, instead of transitioning from nu is equal to 0 to nu is equal to 1, the molecule may jump from nu is equal to 0 to nu is equal to 2 or even higher. These transitions produce peaks at multiples of the fundamental frequency. For instance, if fundamental vibration occurs at 500 centimeter inverse, an overtone may appear near about 1000 centimeter inverse. But overtone peaks may usually much weaker than fundamental absorptions. A good analogy is a guitar string. When you pluck a guitar string, you hear the main tone, the fundamental frequency. But you also hear weaker harmonic tones. These are similar to overtones. Next, we have combination bands. Combination bands occur when two different vibrational modes interact simultaneously. Instead of absorbing energy corresponding to a single vibration, the molecule absorbs energy equal to the sum of two vibrations. Mathematically, we express this as nu combination is equal to nu1 plus nu2. For example, if a molecule has vibration at 600 centimeter inverse and 800 centimeter inverse, a combination band may appear near 1400 centimeter inverse. However, not all combinations are allowed. Quantum mechanical selection rules determine which combinations can occur. There is another related phenomenon called difference bands. As the name suggested, these occurs when the observed absorption corresponding to the difference between two vibrational frequencies. This can be expressed as nu difference is equal to nu1 minus nu2. The difference bands are usually weaker and less common than combination bands, but they can still appear in complex spectra. Finally, we encounter a very interesting quantum mechanical effect called Fermi resonance. This occurs when a fundamental vibration happens to have nearly the same energy as an overtone or combination band. When this happens, the two vibrations interact with each other. Instead of appearing as a single peak, the absorption split into two peaks. Their position shifts slightly and their intensities change. This phenomenon is called resonance coupling. Fermi resonance is especially important in carbonyl compounds where overtone vibrations can interact strongly with the fundamental carbon double bond oxygen stretching mode. If you are aware of this effect, you might mistakenly interpret the split peaks as two different functional groups, but in reality, they arise from the same vibration interacting with another vibrational mode. Recognizing Fermi resonance is therefore an important skill for advanced spectral interpretation. Let us summarize what we have learned today. We explored how different functional groups produce characteristic air absorptions. We saw examples including methyl groups, anhydrides, amino groups, nitro groups. We observed that asymmetric stretching vibrations occur at higher wave numbers than symmetric stretching. We also examined additional spectral features including fundamental absorptions, overtones, combination bands, different bands, and Fermi resonance. These phenomena explain why IR spectra often contain more peaks than expected. Understanding these effects helps us interpret spectra more accurately. Infrared spectroscopy may appear simple at first glance, but as we dig deeper, we discover layers of fascinating quantum mechanical behavior. The ability to recognize these patterns is what transforms someone from a beginner into an expert spectral interpretation. In our next lecture, we will connect vibrational spectroscopy to classical physics. Specifically, we will use Hooke's law to understand how bond strength and atomic mass determine the frequency of molecular vibration. Thank you for watching. I will see you in the next lecture.